Okay, we just finished part three. We're gonna go on to part four. Let me dismiss my image and we're gonna discuss ocean tides. Actually, we're gonna discuss more than that. We're gonna discuss black holes and other things, but there was too little to separate it into more parts. So we're gonna do all this in part four. Of course, here in San Antonio, Texas, we're landlocked, so I don't ever see the effect of tides. Uh, I have family that lives on Nassau Bay, right on the lake, and I'm sure they do see the tides. But the difference between ocean levels at different times of the day are called tides. A low tide is the water kind of, well, it's lower. It you'll see from the graphics that it's kind of bulged out to other sides. And at high tide, it's higher than normal. And in some places, it can be several meters. There are typically two high tides and two low tides each day. And there's a page with a tide calendar in your textbook. I encourage you to, you don't have to study it. I'm not going to ask you questions on it or anything like that, but I think it's a nice graphic. It has nice graphics that shows what happens with the tide calendar. You have two high tides and two low tides every day. Okay, ocean tides are caused by the gravitational attraction of the moon and the sun. Unequal tugs on Earth's oceans causes a stretching effect that produces a pair of ocean bulges. Because the two bulges are on opposite sides, high tides occur approximately every 12 hours. And it's approximate. If you look at that calendar, you'll see that it does advance. I think about an hour or so, which is the moon. You know, that's a it every day. It's a little. It lags a little further behind. You know, there's about 29 and a half days between full moons or new moons, depending how you want to call it. But you can see that the moon over here is it pulls the the water outward. It's a gravitational tug on the water that causes the tides. And we can see during the new moon, this would be the new moon when you don't see it, and the full moon when you do see it. The effect of the moon and sun add up in causing more pronounced spring tides, what we call spring tides. When the moon is halfway between a new and a full moon, first quarter and third quarter, the tides due to the sun and moon partly cancel each other, causing less pronounced neap tides, what they call neap tides. So here you get maximum tides, and here you get weaker tides. You do get tides, but they're not as pronounced. Okay, interaction between Earth and Moon is acting at a distance. How do they interact without touching? One way to think of this is Earth is surrounded by a gravitational field. The moon interacts with its gravitational field. If you ever play with strong magnets, you can feel that if you just approach one another, they start to attract each other. There's a magnetic field that pulls opposite sides of the magnet, north and south, together. Certainly, if you were to have a north and a north and you try to push them, you can certainly feel the resistance of pushing them towards each other. That's a gravitational field. I'm sorry, that's a magnetic field, but similar to what a gravitational field is like. Gravitational field is an alteration of space around Earth with any object with mass. The gravitational field is just an example of a force field. Another example is a magnetic field, what I was just talking about. Pushing two like poles of a magnet together, you'll feel the resistance where you can't push them. And the opposite, if you have a north and a south, if they're strong enough magnets, you better get your fingers out of the way because they can't smash them. I used to work with nuclear magnetic resonance, and you have strong magnets there, And to move the magnets around, we would use gloves, because if you got your fingers caught between those magnets, it was going to give you a good blood blister. Okay. Gravitational fields are represented by field lines radiating into the object. So you can see all these lines, and they're all directed perpendicularly to the surface of the Earth. These are the gravitational field lines, and you can notice where the spacing is greatest is where the gravitational field is the strongest. Notice as you get here towards the outer edge, the spacing it's spread out, so the gravitational force is not as great. The inward direction of the arrows indicate that the force is always attracted to Earth. The crowding of arrows closer to the Earth indicates that the magnitude of the force is larger closer to the Earth. That's what I was talking about. The density, the large density of the lines on the surface of the Earth. Okay, the gravitational field decreases to zero at the center of a planet. Now that's not quite true with our planet, because the density of the planet Earth changes as you go through layers. So this is for an ideal planet has a uniform density, which again the Earth is not. It's not uniform density. If you are inside the planet, then the pull from the mass beneath you is partially counteracted by the pull from the mass above you. So if you were right in the center, your gravitational field would be zero. As you move out, it increases linearly. And then once you reach the surface, it's the same inverse square law that the gravitational force, the gravitational field falls off. Outside the planet, the gravitational pull decreases as the distance squared, dropping to zero at infinity. Okay, this is a completely hypothetical thought experiment. Suppose you dig a hole through the Earth to the other side and jump in. We're going to ignore the fact that that's not possible because of all the inner core and the very hot magma. This is just for a thought experiment, drilling a hole all through the Earth. As you fall, your acceleration downward the center will decrease as your depth increases. At the center, your acceleration will be zero. Your speed will be maximum, but your acceleration will be zero. Past the center, you will be pulled back, slowing down. Because you acquire sufficient speed at the center, ignoring air resistance, you would reach the surface on the other side. So what this looks like, if you could imagine, I'm trying to remember if I did a Walter Fent demonstration with a little spring on with a little mass on a spring on either end. Is the spring goes up, it turns, it's a constant change of kinetic energy and potential energy. As it goes up, the kinetic energy is going to zero because it's stopping and reversing with your maximum potential energy. And then you start going down and it turns on all into kinetic energy. That's where you would be at the center of the Earth. I'm trying to do an analogy here. And then you would go down and you would go to spring potential energy and go back up, and you would oscillate. And the same thing is true here. You would go, I'm going to dismiss this, you would go from having full gravity to accelerating, and your velocity would be greatest here, but your gravitational acceleration would be zero. Then you'd come up here and you would slow down, but increase your gravitational potential energy, as it were. And then, so you would just basically oscillate back and forth if this were even at all possible. And it's not on the Earth, not on this planet Earth. Okay, let's, there we go. Now, Einstein's theory of gravitation, the gravitational field is a warping of space-time by any mass. analogy, a massive ball making a dent in the surface of a waterbed. You can look at some of these. I'll try to post a video of some of these experiments that are done with a metal ball and a rubber fabric stretched like a drum. They're interesting. I'll try to include one. You have this massive ball making a dent on the surface. The warped space-time affects the motion of other objects. So if you were to roll a marble along the edge here, it might make it all the way across without being pulled in. But as it's if you were to throw it like at an angle to where it gets caught in the little indentation, it would go around and round and round and round, and then finally fall in towards the ball on the bed. It gravitates towards the dent in the on the surface. Okay, black holes. When a star exhausts nuclear fuel, it shrinks so that its mass becomes concentrated within a smaller radius. So here they show an indestructible person standing on a shrinking star. Because if you weren't indestructible, you'd burn up. I think if you look at the original Iron Giant, the book, not the Brad Bird cartoon, which is a great cartoon in my estimation. The Iron Giant, I think he somehow I don't know if he's like on a sun and burns himself to defeat his enemy. Anyway, look it up. It's a fun little book. Again, in my opinion, the movie's better, but so be it. So this is an indestructible person standing on a shrinking star. If the shrinking star goes to half its radius, you are remember it's a 1 over r squared. So if it's half the radius, it's quadruple the force. Well, if it's shrinking, wouldn't it be less mass? No, it's the same mass. It's the same density. It's just being compressed. It's not losing any mass. It's just being compressed. So it's just as much mass as when it had the larger diameter. So the gravitational force on the surface increases, but the force still equals G times M1, M2 times D squared. So the D has been cut in half, so it increases to 40,000 newtons. When D decreases, F increases. And you can see that the distance that has decreased, so it's quadrupled. Oops. I think that's okay. Black hole. When a collapsing star becomes so small that its gravitational field exceeds the threshold for allowing anything, even light, to escape, a black hole is formed, trapping everything inside forever by warped space-time. Black holes do exist. They've shown them. I don't know that. I think it's in the book. They show you the first photo ever taken of a black hole. I don't remember what spaceship took it. It's not the James Webb, because it must have been the Hubble. It's in your book. So let's see. What would happen to Earth if the sun became a black hole? It would break away from the Earth would break away from the attraction of the sun. It would be pulled into the sun. It would become a black hole too. None of the above. And the truth is, it's none of the above, because if the sun were to collapse, it would have the same mass, and it would have the same center point. So the distance between the two would be the same, and the gravitational attraction would be the same. So none of the above is the answer. Using the universal gravity equation, we see that if no mass changes, if it just becomes more dense with the same mass, and the center-to-center distances do not change, then there would be no change in the gravitational force between the shrunken sun and Earth. In truth, the star collapses into a black hole after it's swelling to tremendous size and then eventually exploding in a supernova. These events would destroy the Earth. It would be consumed by the heat of the exploding sun, which probably will eventually happen, but not in our lifetime. We don't have to worry about it. Millions of years. Okay, a wormhole, a distortion of space-time. Instead of collapsing toward an infinitely dense point, a wormhole opens out again in another part of the universe or in a different universe. So even though they have photographed black holes, and we know black holes exist, no wormholes have ever been discovered. It's a theoretical physicist's dream. Okay, universal gravitation. Everything attracts everything else. For example, the Earth is round because of gravitation. All the parts of the Earth have been pulled in, making the surface equidistant from the center. There are unresolved mysteries about gravity. The universe is expanding, accelerating outward, pushed by mysterious dark energy. Also, galaxies exhibit extra gravitational pull attributed to mysterious dark matter. So they're in pursuit of this dark energy and dark matter, but it hasn't been found yet. Okay, and that's the end of the chapter. We'll end it here.